Today the topic of the meet is images that sound, composing images and sounds on a single canvas. So a little bit about the session. So the people in this meet. So basically, Ziyang will be hosting this, and he'll be talking about diffusion models to generate spectrograms that look like images, but can also be played as sound. Spectrograms are 2D representations of sound that look very different from the images found in our visual world and natural images. And natural images, when played as spectrograms, make unnatural sounds. In this paper, they show that it is possible to synthesize spectrograms that simultaneously look like natural images and sound like natural audio. They call these spectrograms images that sound. The approach is simple and zero shot, and it leverages pre-trained text to image and text to spectrogram diffusion models that operate in a shared latent space. A little bit about Ziyang Chen. He is a third year PhD student at the University of Michigan, advised by Professor Andrew Owens. His research interests lie at the intersection of multimodal learning and self supervision, specifically exploring the relationship between audio and visual modalities. During his PhD, he has interned at Codec Avatar's lab, Meta, and Worky. So, thank you, Ziyang, for taking the session, and please take the session forward.
Yeah, thanks Niels for the introduction. Hi everyone, I'm Ziyang. Today I will talk about my recent project called Image and Sound, composing images and sound on a single canvas. So this is joint work with my lab mates Daniel Gung and Professor Andrew Owens. So there is some more information about me. I'm a third-year PhD student advised by Professor Andrew Owens, and my research so far has been focused on multimodal learning and self-supervision, especially starting sight and sound. So I had interned at the Mathematics Lab last summer working on neural acoustic field and spatial audios, and I'm currently interning at Adobe Research with Prem, Brian, and Justin working on audio visual generation models. So let's start talk about the project. So the spectrograms, a lot of people might know it, is a 2D visual representation of the sound. The waveform, after a short time Fourier transform at the log-mail conversions, is creating the spectrograms that plot the sound energy within the different frequency over time, where the low frequency representing the low pitch and high frequency energy are high pitched. And this is how it sounds like. However, those spectrograms are abstract images that look quite different to natural images. But what if we run image capture models such as flip-tooth? They will get results like a black and white photo of a window with a curtain. This indicates that the statistical similarity between the natural image and the spectrograms. Therefore, we ask whether we can find or creating the examples that lie in the intersection of the image and audio distributions. We call those examples images sounds that look semantically meaningful when viewing as image, but also sound meaningful when played as spectrograms. So artists have been exploring the spectrograms art towards that goals. They manipulate their songs to display a desired image when visualizing as spectrograms. This is one of the famous examples by Apex Twins. He embedded his face in his song's formulas. Other artists also put musician Easter eggs into their soundtracks. Venetian proposed editing spectrograms to including an image of his cat in his album Songs About My Cat. The 9-inch Neil using an image in the spectrograms of My Violent Heart as the album cover art. However, those soundtrack, as you can hear before, that more sounds like a random noise rather than the nature sounds. So in other words, those examples don't really lie in overlap distributions between those spectrograms and the image. So different from them, we aim to find and generate signals that are as natural as possible in both modalities, such as towers are spontaneously sounds like raining bears, or image of dog make dog bark sounds. Those are examples that we created. So how do we create those examples? This generative modeling problem is challenging because it's required to model a distribution that's induced by two very different data sources. And especially there's no relevant paired data available for us to train a model to do it. So to solve it, we propose it as a multi-model compositional generation task, and propose a simple zero-shot method that can compose off-shot text-to-spectrograms and text-to-image diffusion model from two different modalities. So diffusion model iteratively denoising standard Gaussian noise xt to generating clean example x0 from some learned data. At time step t in the reverse diffusion process, the noise predictor taking the intermediate noise samples and the conditional y, such as text prompt, a photo of cat, to estimating the noise to be removed. The later work about latent diffusion performed the diffusion process in a latent space using pre-trained encoder decoder pairs to translating between pixel space and latent space. The latent space is typically more compact and information dense, which makes diffusion in this space more efficient. And our approach using pre-trained LDM with the same latent space, which is pretty important to jointly denoising those shared latents. So recent work has been started composing different visual components using diffusion models by maximizing the multiple conditional likelihoods. This is an example from the Liu's paper for the compositional visual generation with the composable diffusion models, where you can jointly contain the charge, lightning, pink sky together by creating example content of the contents. So inspired by those prior works, we ask if possible to compose the distribution PV from the image expert models, which we're learning from the visual data only, and the distribution of the PA from the audio expert model that's learned from the spectrogram data to produce an overlapped distribution from a product of those expert model, which we call the PAV. So then images sound examples are sampled from that overlapped distribution that's composed from the different modality in that case. So we regard our method as a type of multi-model compositional analysis where given a noisy latent xt, we apply the audio diffusion models guided by text prompt such as bear ringing to compute the audio noise estimator epsilon loon A with classifier-free guidance. Similarly, we can apply the image diffusion model on the same latent noise, noise latent, guided by image text prompts such as castles with bear towers to compute image noise estimates epsilon v. We're using diffusion models with shared latent space, so that allowed us to composing two noise estimates from different modalities together in our case. We obtain the multi-model noise estimates epsilon had by a weighted average over them and use it to obtain a less noisy latence xt minus 1, where the epsilon lambda a and lambda v are the weights for the noise, and then we can use it as part of iterative denoising process. By iterative denoising latence, we obtain the clean latence dt. Then we're using decoder to obtain the spectrograms and convert it to a waveform using vocoders. We know that all the model we use above are pre-trained. We don't retrain any models on that all. So our generated image can also be colorized with off-the-shelf colorization models. We're using the factorized diffusion and guided colorization with text guidance. There is one example. So also, since there is no really prior work to solve these problems, so we also propose the other two baselines to creating the image and sound. The first one is in-print baseline, where we print the image into spectrograms. We're using the image and audio diffusion model to generate the image and spectrogram respectively, and then simply subtract the image from a spectrogram, which we're creating those examples. Another one is that based on the multi-model score distillation sampling inspired by the diffusion illusion from Ryan, where we jointly optimizing the image using SDS loss from the image and audio diffusion. And since this approach is optimization based, where it will be taking a few hours to getting one sample, and our method only taking 1 to 10 seconds since it's inference only approach. So for our method, we're using the stable diffusion windpoint for V1.5 as the image diffusion models. And for audio diffusion model, we're using AU fusion, which fine-tuning the stable diffusion 1.5 on the log mail spectrograms so that we can have the shared latent space. So for the vocoder, we're using hi-fi GAN, pre-trained hi-fi GAN to convert spectrogram to waveforms. And we jointly denoising for 100 step and with audio denoising only for the 10 step as a warm-up start. We perform some quantitative evaluation on the generated results. So examining how well generated examples that match the provided text prompt for each modalities. We're creating two sets of text prompt and randomly pair them up and using clip and collapse score to evaluate them. We report the stable diffusion and AU fusion as single model models to present lower and upper bounds. And as you can see here, our method approached the baseline in both metric significantly better on that case. And we also, things like, it's like only using the automatic tracking is not enough to evaluate ours in the artistic side. We also perform human study with 2 effects setups to let users to choose a better examples in respect to audio qualities, visual qualities, and audio-visual blending, which alignments between those two. And as we can see from the results, human evaluator consistently rate our examples are better in those 3 factors. We also should have some like qualitative comparison with the baselines, where here is 3 videos from the SDS baseline, in-print baseline, and ours, where for the SDS baseline, it's unlikely to generate a saturated image, but also sounds not that good. Well, the in-print baseline, while they can creating a good-looking image with a clear pattern, but because it subtracts the energy from sound spectrogram directly, which crops the sound in the case. Also, we find that SDS baselines sometimes fail to optimize the objective, which should lead to very bad results. Which are completely random noise in that case, and also visual components are actually not showing up. Well, for input baseline, well, sometimes they can generating very good image and look sounding very good. But if you really look in carefully, the two signals are actually separated, presenting in the same image. So, which don't have any alignment between those two. Well, for our method, surprisingly, our method can blending the audio and the visual signal into the same canvas in a very natural way, where the sound energy, the higher sound energy, become the flowers or something else in the canvas, which makes things looks very good. There are some more Cohere results from our multimodal denoising method. So there are more generative grayscale image from all of those examples. We can see the visual and audio signal are blending together in very surprising ways. There might be some audio and video off sync because of Zoom sharing in that case. So also doing a cycle consistency check, note that we're using hi-fi again as a neural vocoder to convert waveform, given that the spectrograms are out of distribution. One concern is that our model might find that adversarial examples that against the vocoders. To address these concerns, we conduct a cycle consistency check by recoding the neural vocoders, predicting waveform back into the spectrograms by performing the same STFT operations. And as we can see here, the recomputing spectrograms are very similar to the original spectrograms, with only slightly less sharpness and some blurred textures. It means our method truly creating those examples or those audio examples which are really spectrogram. Also, our method is not perfect. It's also leading to failure cases very often. Because some of those failures may be due to the strict constraints of the problem, since related examples might not always existing at the intersection of the both distributions. Such as the first case, it has good audio qualities, but the visual results are not quite clear. And the second one has very good visual qualities, but the sound is kind of broken in that case. Also, another limitation of our method is that it cannot generate an example that have both high fidelity audio and image because of distribution gap between those two modalities. Since especially we are trying to representing both signals together, but using one image. So please visit our website. There's more example on them, and also we providing code, and you can implement your own prompt and playing with animation we have. That's all for the image sound project. I also have some interesting work working on audiovisual spatial correspondence and multimodal learning, including touch. And in the local sound localization motion project, we jointly learn the sound localization and camera rotation in a self-supervised manners and with multi-view egocentric audiovisual data. Here is a simple demo for the project where we're estimating sound angle and camera rotation using our learned model. And thank you for listening, and I'm happy to take whatever question you have.
Thanks a lot, Ziyang. So I had one question. So you said that there are multiple, obviously, images that can be formed via the audio that you're providing. So you said that there's an intersection, which is the part that actually works. So my question would
Yeah.
be, how do you find this intersection?
Yeah, so we find the intersection by jointly denoising them using two model, right? Just like we are not, we kind of like we cannot directly find the distribution because like we don't really having such such like paired data for us to formulating joint distributions. But in other cases, we are able to sample the distribution, we are able to sampling the examples from these distributions by our methods. So just like you can, because like diffusion model kind of like denoising them towards that distribution for the generated image. But if you're denoising with those both objectives, and then they will be likely to denoising into the distribution that we're looking to find.
Okay, got it. Thanks for the answer.
Is there any other question?
I think I'll ask one more question I had in my mind. So basically, if if we want to input multiple audios, or maybe provide a sample audio, not just a prompt, how do we do that in this scenario?
Yeah, in our cases, we haven't been really explored the existing audio directly because we because like we're currently just like finding the distribution between both of them are pretty hard. So if we're given a hard constraint for the existing examples, they are more likely to just like only fail in the audio distribution or image distribution only. In that case, you're probably not able to find a good image like sound example so that can contain the image. But we could do SD editing where for you given the audios, you're adding the noise to it, then you're denoising from a time step like 90% of them. Then we're likely to including the visual components into image, but it won't be as good as you denoising them from the random noise.
Okay, thank you for the answer.
I guess that's all for today. Yeah, thank you everyone for coming and invite me for the talk.
Thanks a lot for taking this session, Ziyang. And
yeah,
yes, we wish you all the best in your future endeavors. Thank you.
Yeah, thank you. So I think they recorded the video, right?
Yes, I will just.